Hello, hello. Hi, Rupert. Hydrate? Okay, let's hydrate. Um, how's everyone doing? Let me put on the musics. It's been a rough week for me. Like, I'm definitely happy that I started this project slash channel, whatever. Um, it's served as a general guidance of a bunch of things I wanted to do, anyways. So I've been drawing, plotting, planning, getting into video editing. Okay, Rupert says he's ready. Um, oh no, what happened? Anyway, anyway, so I left homework last week. We made our leap into first order logic. We explained briefly replicacy BBC. Yeah, but in a good way. I mean, just I don't usually have this many things I want to do at once, and covering so many different skill sets. Like making a hobby, like making a streaming channel as a hobby is very demanding because it requires graphic design, composition, audio. You need to know several software programs, even get a little bit familiar with intellectual property laws. It's really a multidisciplinary thing. It's very, as in the early 90s we used to say, a very multimedia project. That's why it's particularly busy. And the things you don't know how to do on your own, you need to get money to get someone else to do it for you. Yeah. And if not a team, at least money to pay people to. So I can do a lot of things, but I cannot compose. So I've been struggling with that particularly. Anyways, I may have a new English student soon. Yeah, you've been very helpful. Don't worry. As we do. So let's get into the actual homework thing. So the point of this exercise is not to get everything right. Just get our brains working with the idea of working with predicate logic. Almost every sentence that we model through first order logic or predicate logic has structure. By that I mean some sort of logical connective working on it. While when we were working with propositional logic, I mean, propositions are just blunt statements, so we just had a lot of things BP. So a lot of the inner complexity of a single sentence we could not capture through propositional logic. And now through predicate or first order logic, we can do that. So let's go over some of the easier examples. I think that the first four are like warm-ups. So we want to formalize. We want to turn a sentence that is written in plain ordinary language, in this case English, to a formal language in which we cannot rely upon the standard meaning of words, and we need to express whatever we can express within the structure of the system. In this case, through logical connectives, quantifiers, and so on. So, we have anyone who is persistent can learn logic. This anyone does not refer to a particular person. This refers to any entity, and I'm using entity in a very philosophical way, like the broadest possible category of thing that is an entity. Any entity that has the first property, in this case being persistent, has the second property, in this case the capacity to learn logic, which in English we say can learn logic. So what I can recover from this statement in my formal language is, if you fulfill the same criteria, then you fulfill the second criteria. And this applies to everyone. Remember Gary Oldman. Everyone. Literally everyone. For all of the objects in the known universe. We'll get to what it means to be an object in the known universe in a bit. So anyone who has the first property then has the second property. Good. That's it. That's all we can really say about this. We can dress up the statement, say P is for being persistent, L is for can learn logic, but we don't really care about the meaning of the properties. We only care about the relationship between the properties. The meaning of the properties or the predicates is a non-logical affair, at least in this system. No politician is honest. Very similar to the first one. What this statement says is that if you fulfill one property, then you do not, negation, fulfill the second one. So, for everything in the universe, if that thing is politician, then that same thing, that same X, does not have the H property. What is the H property? Being honest. So I noticed, Rupert, that in your formalization, you added a negation to the property being honest, such as it cannot be honest. We can actually express the cannot part through a logical connective. In this case, the negation. So that's what we do. Instead of saying is not honest, I say is honest and then add a negation. Also, there are two ways in which we can do this. This sentence and this sentence are equivalent. Let's think a bit about why. This sentence says, for everything in the universe, if they are a politician, then they are not honest. This sentence says, there doesn't exist anything in the universe that is simultaneously a politician and honest. So these two are ways of expressing the same state of affairs. It's fine, Rupert. I mean, I'm not grading you. This is just to get people into mathematical thinking, and you're getting there. You're getting into mathematical thinking, and that's the goal of this mission. So one interesting thing about the fact that we can express the same state of affairs is that we start getting a glimpse into what first order logic calls meaning. The meaning of a formula in first order logic rests upon what makes that formula true. True with an apostrophe. I'll explain that apostrophe in a bit. But the thing is, this sentence and this sentence are both fulfilled by the exact same set of conditions. Think about it. What will make this sentence false? How do we falsify this sentence? What is a valid counterexample to the statement, no politician is honest? What will you need to show me so that I have to retract my statement? If I say no politician is honest, what supposedly empirical evidence will prove me wrong? What will be a counterexample of the sentence, no politician is honest? I'll give you people on chat and on the video archive some seconds to think about it. Some politicians are honest. Exactly. You got it. If you show me at least one thing that has the first property, but not the second, so being a politician, being honest, that will go against my truth conditions for this sentence. And it is exactly the same thing here. Because what is the negation of there doesn't exist a thing that is both a politician and honest? Basically, the sentence without the negation. There exists something which is a politician and honest. Which is what Rupert just said in chat. So this sentence and this sentence, they are equivalent. They are two different ways of expressing the same state of affairs. Not all birds can fly. So, not all things that are birds are things that can fly. Alternatively, there exists a thing that is bird and not fly. Not can fly. And now in exercise D, we start to get used to the idea that the predicates or the sentences we're modeling, we don't care about their empirical or factual truth. In this world, at least. All birds cannot fly. That is, of course, false in our world, but we don't care about that. We're just modeling. We are not in the business of interpreting whether statements are empirically true or false. We just analyze the sentence. And this sentence is saying that for everything that is a bird, for every x such that x is a bird, then that x cannot fly. Here I miss a negation. Or alternatively, there does not exist a thing that is a bird and flies. Now, some of the more perspicuous people in chat might notice, okay, but that is structurally the same thing as no politician is honest. Yeah. Just as in this case we talk about P and H, and here we're talking about B and F. But the structure is the same. We're just naming the property something slightly different. But in this system, we don't care about really what does it mean to be a bird, or what does it mean to fly or be able to fly. All we care about is that. Let me see if I have like a free hand. Yeah. All we care about is that there is a group of things And that group of things has, ew, what just happened there? What I want another color. Here we go. All we care about is that there is a thing inside another thing. Yeah, we don't even know what it means to be a subjective truth here. There's no subjects in here. They're just objects. So just imagine that this is the block of things that are B. We don't care about what B means. We don't care that B is named birds. We just care that there's a thing, and there are things in that list. There are things in that group. And we care that, for example, if this were this, all birds cannot fly. All we care about is that the group of B's and the group of F's, basically things that can fly. I have to do it in one. Oh god. Do it in one stroke. Man, this is difficult. Okay, there we go. Yeah, it's kind of an object-based programming, more or less like that. All we care about in this sentence is that these two sets are disjointed. By that we mean that there is no B's in F. All we care about is that there is not a single thing that is both a B and an F. So, disjointed, separate. That's all we really care about. We don't care about the meaning of what a bird is or what fly is. This set of things, this model, makes this statement true, and it also makes this statement true. We just need to change the name of the sets from B to P, and from F to H. Okay, that is the intuition behind all this. Now let's go into some of the more difficult examples. X is transcendental only if it is rational. Here the trick is remembering what only if means. Only if points to the necessary condition. So what we have is, if something is transcendental, then that thing is irrational. It's a necessary component of being transcendental, whatever that means, to be irrational. Are we talking about metaphysics? Or are we talking about numbers? Who knows? All I'm doing is modeling the relationship between two groups. It's fine, yeah. Only if... I mean, it's not that the words can be mechanically translated. I mean, if and only if is pretty much only used by nerds, so that one might be the exception. But it's not that you have to automatically take only if as necessary condition. But it is almost always, it is very strongly that thing. What we care about more than just the words is the relationship between the things. What this sentence is saying is that if something is transcendental, then it is rational. I cannot have something that is transcendental and not irrational. So that is how we model it. That is how we formalize it. Seniors date only juniors. Okay, this one is a little bit more complex because we have a relation. We previously spoke about that properties are limit case for relationships, which is a one slot relationship. A property is a relationship of one thing. And here we have a relationship between two things. Dating. Something needs to date something else. Yeah, that one is fucked. Thankfully, we don't have to care about the problematic age gap. We don't have to interpret what senior or junior means. Remember that we only care about senior and junior as two names for two different sets. That's all we care about. So, seniors date only juniors. So that means that if something is a senior and that thing, that X that is a senior, is dating something with a Y, so then that something being dated by the senior is a junior. Seniors date only juniors. We have two conditions. Something needs to be a senior, and that senior, that same X, needs to be dating something which we call a Y. If those two things happen, then that Y has to be a junior because seniors date only juniors. If anyone can solve the problem, Hillary can. Notice that in this case, the parenthesis does not cover only the inside. If I had to do the parentheses for the sentence, I would have to draw them all the way on the outside. If there exists something that can solve the problem, whatever that means, then the object H can solve the problem. Here, the main connective is the conditional. The existential quantifier, the scope of this quantifier is only until here. It does not cover the entire sentence. I'm glad it's clicking, hell yeah. If anyone can solve the problem, if there exists anything in the solve the problem set, then H is also in the solve the problem set. That's it. We don't care about who Hillary is. We don't care about what it means to solve the problem. We don't even know about what it means to be the problem. Because in ordinary English, when we say the problem, that is an index. That is an identity we can only understand through the context. What the fuck does it mean to be the problem? I don't know. Nobody explained that to me. I do not have that information here. All I know is that there is a thing called the problem. I don't know what that means. And I know that if anyone is in the set of the things that can solve the problem, then Hillary is in the set of the thing that can solve the problem. Nobody loves a loser. That is, for everything that is a loser, then, yeah, you can. There you go. In fact, you need them to be different because if I do this sentence says, everybody who is a loser does not love themselves because it is the same X in both cases. Both variables point towards the same object. And we don't want that because that is a different thing from what this sentence is saying. This sentence is saying is that if you're a loser, for everything that is a loser, then for everything in the universe, It is not the case that, yep, you're getting it, Mr. Krabs. Then for everything in the universe, it is not the case that anything in the universe is in the V relationship, which is love's relationship, towards that X. So for everything in the universe, if that thing is a loser, then nothing in the universe is going to love them. That is the very expanded way of saying nobody loves a loser, which is totally false in this world, thankfully. Nobody in the statistics class is smarter than everyone in the logic class. Another sentence which I find completely tasteless, but I don't have to care about it. I don't have to care about what it means to be smarter. If you want my opinions on how we treat the concept of being smarter, let me put the link to my translation of the perverse ontology of stats. Always need to do self-promo. Here you go. So thankfully, we don't have to care about any of that. We don't have to care about any worrisome implications about what it means to be smarter or blah, blah, blah. We only know that smarter than is a relationship between two objects. That's it. We know that there are two other properties, which is being in the statistics class and being in the logic class. So it is false that there exists something that is in the statistics class, and for everything else in the logic class, that thing in the statistics class, that X, is in the smarter than relationship with any of the objects in the logic class set. Which is a very mechanical, awkward way of saying nobody in the statistics class is smarter than everyone in the logic class. But that kind of rigid, awkward, it's fine, Rupert, it's fine. You can compare and contrast. Now, these are tricky statements. Like, in a ordinary Logic 101 course, we spent at least 2 months doing this. 2 months of 2 classes per week of 2 hours, plus homework, plus tutoring. So it usually takes your first grade philosophy undergrad. So it is minimum 2. 16 hours of class to get through this, and we're trying to get this in 4 hours. So yeah, don't worry about it. It's a different format, and again, this is not a course. This is not graded. This is not going to certify you as someone who knows Logic 101. I do not have that authority. I do not have any institutional backing. What we want to do here is to get people closer to understanding how mathematical logic and reasoning works, because that is an excellent tool for navigating the complexities of industrial life in the cyberpunk year of our Lord 2026. Now, of course, I want everyone to enjoy this as much as I can, but not getting it immediately is not bad by itself. So what we're saying here is a very... Exactly, Rupert, exactly. All that matters is that your skill level gets some XP and keeps rising, if you want to see it that way. So what we have here is a very clunky way of being very specific to what the fuck this means. Nobody in the statistics class is smarter than everyone in the logic class. If we stop for a moment and think beyond the incendiary elements of what are you saying that everyone in statistics class is stupid? No, we don't care about that. We don't even know that stupid and smart are antonyms. That is not part of our programming. All we are caring about with a laser-like focus is this sentence and only this sentence, and we are not going to add meaning or implications. We are not going to read between the lines. We are very explicitly avoiding reading between the lines and introducing information from the social world. So that is why autistic people dominate logic, computer science, and mathematics. We are already intuitively trained towards this kind of communication. In this context, the autistic tendency to stick to expressed meaning is a blessing. It's a benefit. It's like an intrinsic class bonus. So yeah, nobody in the statistics class is smarter than everyone in the logic class. What does that mean? At least in the machinery of first-order logic, it means that there does not exist a single thing that is a member of the statistics class, and that thing is smarter than all of the things in the logic class. That's all it's saying. It is not saying that the logic class is better than the statistics class. It's not saying that people in the statistics class are stupid. No, we only care about this. John hates all people who do not hate themselves. Okay? Very similar to the things about the birds and the politicians. We first select everything that does not hate itself. And I use the X twice. Because this is the same X, it points to the same variable. So it means hating X hates X means X hates itself. Because it refers to the same object. The variable, we do not know who the variable points to, but once we select who or what the variable points to, the substitution is uniform. All instances of X need to be replaced by the same object. That's how variables work in mathematics. We cannot be choosy or lax when we mix variables. So for everything that is not in the hate relationship with itself, that is everyone who does not hate themselves, then John is in the hate relationship with them. So John hates them. Who is them? All of the things that are not in the hate relationship with themselves. Again, very fancy way of saying John hates all people who do not hate themselves. And here, much like the case with Hillary, J is John. Is John a person? Who knows? All I know and care about is that John is a named object, and John will enter the hate relationship against anyone who is not in the hate relationship with themselves. That's it. Everyone loves somebody and no one loves everybody, or somebody loves everybody and someone loves nobody. This one is evil. Like this is an example of why I don't feel bad. Like if people want to skip this one, it's fine. I mean, I recommend they try, but this one is really fucking evil. To jump to assign as a surprise to new students because it's a jump in difficulty. So it is 4 sentences tied together. So let's go with the first one. Everybody loves somebody. Okay? Everything. For everything, there is at least one thing, maybe more, that everyone is in the love relationship with at least one thing. Okay, that's the first one. Everyone loves somebody. I am using somebody and something interchangeably. Because in first order logic, unless I have been explicitly told that there is a special set of people and a special set of objects, I do not make the distinction. I will only represent the information I was given. So I'm thinking a lot like a computer. Unless you tell me explicitly that people and objects are different things, I will not start from that supposition. That is extra information that is not part of my system. So that's why I use something and somebody interchangeably. And no one loves everybody. That means there is not a single thing that for all other things, this special member loves all things. No one loves everybody. What this sentence means is that maybe everyone loves at least something else, but there is not a singular object that is in the love relationship with absolutely all the other objects in the universe. All of them? Yes, all of them. Everyone? Yes, everyone! Now think about what it means to love everybody. It means to love absolutely every object that has been defined in my model. So that is not a really difficult statement. Like, oh yeah, it's not like that pessimistic. It just means that there is not such a single thing that loves everybody. I mean, yeah, that's not a big deal. Third sentence, or somebody loves everybody, which is the opposite of this. There exists a thing that for all other things, this person loves them all. So this is simply this without the negation. Whoops. And somebody loves nobody. So for all things, there exists a thing that thing is not in the love relationship with any other thing. For all X, this Y is not in the love relationship with them. So someone or something loves nobody or nothing. So once I have the 4 different sentences, I just tie them together with conditionals and parentheses. This part says everybody loves somebody and no one loves everybody. And this part says or, somebody loves everybody and someone loves nobody. And the only relationship that I need to do all this is the L relationship, where is the first object loves the second object. This one is also pretty fucking evil. What happens if you try to put that one in a set visually? Yeah, pretty easy. Just let me open GIMP, because it's way easier to draw in GIMP than in LibreOffice, right? I am not using Microsoft. I am using LibreOffice. So which one do you mean? Do you mean K or L? For me to draw visually. K, okay. so let me move over to GIMP. You know, if I had infinite money... Yeah, completely understandable. If I had infinite money, I will hire someone to put like a Professor Layton-ass music right now. Dun, 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 dun. Okay, let me put it on stream. That song is burning my mind. Yeah. Oh wait, might as well copy the text too, so it makes more sense. That depends. That is so yeah, that really messes with me because there's a gray area because music is supposed to be copyrighted by authorship but also by execution. So if you do the cover, you are not like infringing copyright on authorship, these are an execution, but maybe the authors do not want to let you do the cover. It's a mess. I hate intellectual property law. It's bourgeois bullshit, and it's only designed to screw with poor people and enrich the already rich. That's okay. That's another thing. But let's just focus on happy logic things. Okay, so let's work on the first 4 sentences. Let's draw a toy model for each of this. So everybody loves somebody. So if we have our set of things. Whoa, what happened? Oh, low opacity. So we're gonna need stuff, okay? And we are gonna call this set of stuff our universal set. It is the set that contains all the things I'm going to talk about. It's usually depicted with this weird U. For universal set. It's also sometimes depicted with a very extreme X, like that, which I cannot draw, but whatever. I mean, I may need some, like I need to like actually pencil it. Yeah. It's also depicted with like a big ugly X like this. Why not the turn A? Because the turn A is reserved for quantifiers. So in the universal set, we're just gonna have 3 things. Object 1, object 2, and object 3. So everybody loves somebody means that in the relationship set of love, so we know that the love set requires 2 spaces. That means that in this set we're gonna have ordered pairs because we need things that fit 2 empty slots. So in the set of things that are L, I cannot have 1, I cannot have 2. I need to have the ordered pair 1, 2. So I need to make true the statement, everyone loves somebody. So 1 loves 2, 2 loves 1, and 3 loves themselves. So let's check. Everyone, which means every single element of my universal set, is in the love relationship with at least someone? Yes. 1 loves 2, 2 loves 1, 3 loves 3, and nobody is left out. So everyone loves somebody. This is one model. I'm gonna say it. Model. Big letters. In bold. Big. This is a model, a particular bespoke model in which the first sentence, everyone loves somebody, is true. Okay? Now, here's... Okay, no, before I do this question, let's go with the next one. And no one loves everybody. Is it the case that there is not a single element that is in the love relationship with everyone? Yes. 1 doesn't love 1, 2 doesn't love 2, 3 doesn't love 1 or 2. So, there is not a single element that is in the love relationship with everyone. So, this model also makes the second sentence true. And because I want to make both sentences true, because they're joined together by a conjunction, that's it. This sentence is true, and because the main connective is a disjunction, then the rest of the entire statement is true. Okay, so that is one way of making this this 4-sentence chorizo of a formula true. I have made this model makes this true. Yay! But now let's go for the other ones. Or somebody loves everybody. In this model, is it true that someone loves everybody? No, we just went not. In order to make true that somebody loves everybody, I will need to do the following. I will need to define one object that loves everyone. So 1 will need to love 1. 1 will need to love 2. And 1 will need to love 3. Notice that when we say loves everyone, again, we mean it. Everyone, including themselves. Anything that appears, so in this case, this Y also needs to love itself in order to love everyone. So we have the first part true. Okay, there is somebody who loves everyone and someone loves nobody. Okay, let's just say that 2 also loves 1. Okay, 1 loves everyone, 2 loves at least someone, but 3 does not even show up in the relationship of love. So 3 does not love anyone. So 3 will be outside. He's like going. Losers. later, as he goes off to the rest of the mathematical model to be a hater. Or at least not a lover. Because there is not a single ordered pair in which 3 appears as the first element of the pair, then it is true that someone, specifically 3, loves nobody, which is our way of saying is not in the love relationship with anyone, any other member of the universal set. So this model, which we will now call model 2, makes the second part true, which makes the sentence true. Well, will make the sentence true. Okay? So this is one particular toy model. And here's the question I wanted to pose earlier. How many models can we build? Think about it. How many objects can we have in the universal set? Because this is a set, we can have an infinite amount of objects. Not just that, we can have a really big infinite amount of numbers. Let's see if I can still draw alephs. The aleph is first you do a straight line, and then you do a this, and then you do a that. Good enough. You can have aleph 1, or aleph 2, elements in the universal set. And we not only have a possibly infinite amount of objects in the set, in the universal set, we have an infinite amount of permutations. So I just created 2 models, and with 3 objects and one dual relationship, I can have what is the Cartesian product of the Cartesian product is a set of all ordered pairs. So with 3 elements, I have 9. I have 9 possible Cartesian products. But of those 9 possible products, I can take and add one by one. So just with 3 elements and 1 Cartesian product, I can make a finite, a much bigger but still finite amount. But I can have a potentially infinite amount of objects. And that means a potentially infinite amount of permutations in terms of things that can be in or out of the relations, properties, and so on. Now, making models like this, particularly toy models with 1, 2, or 3 elements, is going to be our first semantic tool. But unlike truth tables, models are mostly used as counterexamples. Because in order to prove validity, I will need to provide all possible models that satisfy a formula. And that list of possible models is infinite. That is not something I can provide as if it were a truth table. I do not have a total list of all possible states. In this case, they're not states, they're models. I cannot produce through a mechanical process an infinite list of all possible models that may or may not satisfy a formula. Using some human creativity and ingenuity, I can think of one counterexample if I can interpret the formula and read it correctly. I can then use, okay, so if this formula is saying this, I have to think what model will make it false. Okay. And that works because counterexamples only need one case. Validity is going to require all cases. And this all spans a possibly infinite amount of models. And that is not a task that any human can do. Okay, so this is a model, and the universal set is also many times called domain. Basically, the domain is just the list of objects that we're going to talk about when we make a specific model. Okay, so that is our first intuitive introduction to domains and models. We're going to define them rigorously in a bit. But let's continue with the homework. Okay, Rupert, welcome back. Now, you can fool some of the people all of the time, and you can fool all of the people some of the time, but you cannot fool all of the people all of the time. This one's pretty evil because it tricks people with the phrases some of the time and all of the time. When we talk about time, is time a singular object you can name and quantify? What is a quantity of time? You cannot say hours, minutes, or seconds because some of the time is at least one minimum quantity of time. What is the minimum quantity of time? One Planck length? I don't know. If I interpret time, if I want to add it like the intuitive meaning I understand it and the structure I understand to have through the English language, I'm going to run into trouble. I mean, that is not wrong. The problem is time and the measurement of time are different things. It also becomes more complex because what do we mean when we say all of the time? So here's what I would suggest people to do at home in the first try, and this is already pretty evil. So in this formalization, I will omit the use of time as something I can quantify. So I'm going to need two relationships. X can fool Y all of the time, and X can fool Y some of the time. So there exist possibly two things. One thing is a person, and there exists one thing that can fool the person all of the time. Okay, also, this is something I want to talk about. Who is you? When you say you can fool some of the people all the time, who is this you referring to? I have to do an editorializing choice. I have to ask myself, okay, what does you mean in the sentence? Which is a question that I now sounds fucking weird. What do you mean you no longer know what you means? My brother in Christ, it's 2026. Do you not know how pronouns work? That is real brain logic damage done by real logic. Trying to think of a Bobby's You joke and failed. Yeah, we're gonna play Bobby's You sometime soon after we finish this. Yeah, one of the things you can do, one of the reasons I'm enjoying doing this so much, is that once we finish this course, we can use the tools we learned from this to play Baba Is You like a motherfucking pro. And that's a good reason to learn logic. But back to my weird question. Who is this you referring to? Is this you pointing towards a specific being or entity? Like, when I here say you, I am referring to the people in the chat or the people in the video archives who are watching this later. But here, this you, we do not know the context. This you takes a universal characteristic. It is someone. This you means someone. Someone out there can fool some people all of the time. In linguistic theory, words such as you or tomorrow or today or here, they are known as indexicals, which are words whose referent changes depending on the context and time and person using the word. And something funny happened with this with my English students. I recently went over them with reported speech. So they had to, the exercise went something like this. You talk with Johnny and he told you that he is going to, I don't know, what's a good vacation spot? Oaxaca. With Mary next week. The day after you meet your friend Tom and tell him what Johnny told you. So the exercise is Johnny told me. So notice that here it says Johnny told you. And this you, in the context of Johnny talking to us, well, that you refers to us. But now that we are talking to Tom about Johnny, the index changes. Johnny told me that he is going to Oaxaca with Mary. Actually, I think I messed up. Johnny told you I am going to Oaxaca with Mary next week. There we go. Yeah, that's kind of how it was. Yeah, because this is direct speech and this is reported speech. So, in the original context, Johnny's index of you is Me is now me. Here I was the second person, the second pronoun, and here I am the first person, the first pronoun. I, me. And then Johnny, which was the index back then, he was the first person. And now he is, to me, in the context of the conversation, a he. Because in the new conversation, I am the first person, Tom is the second person, and Johnny becomes the third person. Now, that is ordinary language, that is English. Can I recover an indexical from this sentence? No. I do not think this you is being used as an indexical, as in being two people having a specific conversation. We're not talking about a specific you. This you is a general or royal you. You can fool some of the people, and this you means anyone, some person. You can fool, which I use, there exists someone. Some of the people all of the time, which is F. And you can fool all of the people some of the time, so there exists an X, such that for every Y is a person or a people. X can fool all the people some of the time because of the O relationship, but there does not exist someone that for all people, this person can fool them all of the time. You and anybody referring to one entity in a set fulfilling the same role, we don't know. That depends on the conditions of utterance. That's the problem with indexicals. And honest to God, really fancy people with multiple PhDs have debated the role of indexicals in language for over 100 years. That is what analytic philosophy, that is one of the things that analytic philosophy works in philosophy of language. And while I appreciate the skills I learned in those classes, I have a lot of complex feelings about the amount of complexity and effort dedicated to such study. But that is for another day. Now, what if we want to do this hard mode? What if we want to actually quantify time? Then I have to do this. I have to say, there exists someone. There exists another someone. And for everything that is a time, if there is someone who is a person, and for everything that is a time, one person X can fool the person Y for or during Z. Z being everything that is time. So I end up modeling time as a set full of objects. But this set does not have continuity. It does not have a flow or a direction of time. I just have many things labeled time, which does not seem to recover the structure of time in any meaningful way. Now, I understand these limitations more clearly because there are non-classical logics dedicated to modeling time. They are called temporal logics, and they sound way more badass than what they actually do. They're very cool, but if you like, fucking temporal logics sounds like something pulled out of Morrowind that the Psychic Order is studying. It sounds very cool. Anyways, so yeah, there are a family of temporal logics. They can model this much more effectively and fruitfully. But I mean, this is just us wanting to play the hard mode. Okay, so there is someone who can fool a person during all time, and there exists someone that for at least one time or some time, this person can fool all people all during some time. But And there does not exist someone that for all people and all times, this person can fool all of the people all of the time. So yeah, thanks for the stand up and stretch. If we want to play extra difficult and quantify time, we get this giant ass chorizo of a formula. We're an hour in. Yeah, that's a good moment to stand up and stretch. Okay, stretch and squats. Okay, now that we have stretched, I'm stretching my quads. I'm going to stretch my bands, my inner and outer leg bands, which are a very tricky muscle group that gets trickier with age. Opening my hips. Okay, let's go. Hold on, my knee's not cooperating. There it is. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah. Hope everyone who joins me with the squats dip. So yeah, if I want to quantify time in this sentence, I get this giant ass chorizo or formula, which is not very intuitive, but I just want to show that, yeah, it can be done. But for most people, I recommend this one. Any sets that have the same members are equal. Now, this one is extremely evil, because this is the author teasing us with the first axiom of set theory. We are almost there. We can start to express some properties of set theory. But basically this says, for every two things, if the first one is a set and the second one is a set, and if everything that is an element of the first one is an element of the second one, if and only if, so if you're a member of the first one, you're a member of the second one, and if you're a member of the second one, you're a member of the first one. If it is fulfilled that they have the same members, then the first set is equal to the second, and the second is equal to the first. Now, this is very awkward, isn't it? That we don't have, like, we want to say that two things are equal, and we have to do this janky stuff. Keep that in mind. We'll deal with it soon. Anyone who knows Julia loves her. This is a very simple example, like basically a freebie after the torture of the previous ones. For all things, if they are in the knowledge relationship with J, then they are in the L relationship with J. If you know J, then you love J, and J stands for Julia. Which, now that I think about it, if we interpret Julia as Yuria, which is possible because Japanese, this becomes the plot of Feast of the North Star! Spoilers. But it's too funny to pass on. There is no set belonging to precisely those sets that do not belong to themselves. Yeah, so pain, easy. Torture. Thankfully, the last two sentences are the same. There is no set, there is not a thing such that this thing is a set, and for all other things that are a set, and they are not member of themselves, then this set, is a member of them. So, take the entire universe of your model. Look for the things that are sets and do not belong to themselves. Then, there is not a single thing that belongs to them. There is not a single set that belongs to those things and only those things. Now, did I mess this up and is this a biconditional? It's irrelevant because it's fulfilled. I mean, it's kind of relevant because being a member of is something that we have to express through a binary relation, and we may want some more structure out of it. But the funny thing is that the next sentence is almost the same. It's just that here we're talking about barbers and men, and here we're just talking about sets. So there does not exist a barber such that for all the other things that are men and do not shave themselves, then this barber, this X, shaves them. There is no barber who shaves precisely those men who do not shave themselves. But if you notice, it is the same structure here and there. This is a nod to Bertrand Russell's paradox, which crashed Frege's naive set theory. And this is also a good example of how Raymond Smullyan, who we love in this channel, does his puzzles. He first has like some abstract theory, but hey, we can just make up a story about the things, and if the structure is the same, you're still learning. Yay! Now, this is not homework, but it's the next section of the book, and I wanted to do it anyways. So this is the reverse. We take formulas and then we write them in English. Within a Smullyan mode, that is a fucking great idea. That's an absolutely great idea. I'm gonna get drawing. On that right after this stream. So, we have how it's written in the book being Mendelssohn. Introduction to Mathematical Logic by Mendelssohn, which is the book we kind of mostly used. And okay, so we have the formula, the dictionary. So when we do formalization, this kind of thing where we say this letter means this letter means that, this object, blah, 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 we call this the dictionary. So the dictionary is M of X means X is a man, W of XY means X is married to X is married to Y, and U of X means X is unhappy. Now, I don't like this syntax very much. We can simplify it to this, and also I prefer using ampersand to up. Like this. Look, sorry. I spend a lot of time with people who write fan fiction, so my brain is garbage. But this is the top symbol, while the disjunction is the bottom symbol. So I much prefer the ampersand to the top. Yeah, don't laugh. I know why you're laughing. Don't laugh. So for every x, if x is m, and for every other thing that x is not married, and if it happens that x is not married to any other thing, then x is unhappy. So I will translate it to all men that are not married to anyone are unhappy. The parentheses are not necessary. I just add for extra clarity, to be extremely diligent. Yes, most people understand that being married implies being married to someone. But once we have caught the cyberbrain autistic mode, for all my Ghost in the Shell fans, if we are not explicitly told that being married is being married to someone, that is, that being married is a binary relationship, then we will not know. So we need to make it explicit. So all men that are not married to anyone are unhappy. This is, of course, false in this world, but whatever. So second example, where b of x, see another, I don't like b of x because it's very visually similar to the all symbol, but whatever. B of x means x is an even integer, p of x means x is a prime integer, axy means a equal to y, and b denotes 2. So this sentence simplified to our lighter syntax made for humans. Like, this is very good if you're a computer. There's no room for ambiguity. Everything is properly closed by parentheses. But visually speaking, this is much neater or simpler to read for humans. And we are, so far, here humans. So for everything that has these two properties is equal to 2. So everything that is both an even integer and a prime is identical to 2. Or if we simplify it even further, 2 is the only even prime. If you are something that is both an even integer and a prime, then you have to be 2. That is what this sentence structure is saying. And that is a fancy, very mechanical and awkward way of saying that 2 is the only prime that is even. It is the only natural number that fulfills those two properties at the same time. So this is an idealized definition of an object. Okay, third example, where I means y is an integer and Lx of y means x is less or equal to y. So in our simplified syntax, this means there is no such thing that is an integer, and for all other integers, the first integer is greater or equal than the rest. That, again, is a very complicated way of saying that there is no greatest integer. There is no integer that is at the top in the greater than list or order to all the other integers. There is always someone who is greater than, greater than, greater than, greater than. If you think, okay, no, I found this one, this has to be on top, never mind. You can just apply a function called the successor function and you get the next one. So what is the point of all this? The point of all this, especially when it comes to mathematical thinking and very rigorous logic, is that when someone who has installed the brain damage, the logical brain damage, and fully integrated it to their mental operative system, and I'm being very metaphorical, I'm not saying that brains are computers, but once you have very extensively familiarize yourself with this mode of thinking, mathematical thinking, once you hear a sentence, one of the main tools you have to understand the sentence is what will make this sentence true. What is this sentence implying in terms of the conditions in which it could be true? If I read something that says there is no greatest integer, and I am not particularly careful, I just, I guess, yeah. But once I have the logic bug installed, and I am really into this, okay, I stop and ask myself, what does that mean? What does it mean to say that there is no greatest integer? Okay, what makes that sentence true? That sentence is true if I cannot find or define an integer such that for all the other integers, this one, the one I'm talking about, is the greatest among them all. Is at the top of the greater or equal than relationship than all of the rest. And thus, when a mathematician reads this, then they analyze and they think this, and they eventually get to this idealized statement that is free from ambiguity, from all human concerns about the meaning of words or the material reality of the world, for good or for ill. This, I believe, is at the core of mathematization. Or at least what is known as pure mathematics. But this skill, this idea of analyzing sentences in terms of their truth claims, is incredibly useful for many other disciplines, including philosophy. It is not the only way or the best way to analyze sentences. This is a very philosophically contentious statement, but I'm willing to defend it. Not all language is meant to be verified. Not all language is a correspondence from words to reality. That is a personal philosophical stance of mine and of many other people. I mean, it's not particularly unpopular. But there are some people, especially in the philosophical tradition, that follow these systems, that do believe that the main or the exalted or even the only function of language is to correspond a sentence to reality, as if sentences were some sort of images of the world, and that the structure of sentences is somehow mirrored in the structure of things. Okay, there are some philosophical schools that think of that. I studied under those schools extensively for quite a many years. And while I like thinking that way, and it's a very useful way of thinking for mathematics, for programming, for video games, I don't think it's the only or the best use of language. Going back to the essay, VODs will get different after this. I'm saying the importance of giving this kind of rigorous structure to general thinking, but special argumentation. Yes, that is why I'm doing this after those VODs, because I mean that's just for general use. But people who really want to have like a very rigorous, structured form of debate can use many of these tools of mathematical thinking to complement their thinking. Okay, now this one is also really fucking evil. I simplified the notation that the book uses to our more visually appealing syntax. So the first sentence is, there exists a P, so that is something that is a person, and for everything else that is a person, this first person hates them. So one will be, there exists a person and they hate all other persons, including themselves. Again, what is in parentheses is not necessary. I just added to be really, really explicit. Hating all persons necessarily, logically, implies hating yourself. Which is a very funny lesson for the people. I hate all humans. Yeah. And they hate themselves, too. Second sentence being, for everything that is a person, then there is for other people hate from the first to the second. So in a very awkward, stilted way, we can say, if there are people, then all people hate all other people, including themselves. Or, simplified to more readable English, all people hate all people. Boo! Get the fuck out of here with that misanthropic shit. Now 3. There exists an X such that X is a person, and for all other people, this person hates all people if and only if they hate themselves. So, there is a person, and for all the other persons, this person hates them if and only if they hate themselves. That is what in Spanish we call lo gañol. Still can't get predicate letters? What seems to be the problem? Okay, I think this is going to be easier once we cover models, which we'll do in a bit. So in simpler, not logical English, is there is a person who hates everyone who hates themselves. What it is this becomes this, becomes this. Ever more specific and formally rigorous forms of expressing the same idea. Okay, and this is also a mess. I just gotta go back and read the catch up. Yeah, don't worry, Rupert. We have time. Also, I'm gonna tell you that, once you go back to school, which is gonna be delayed because UNAM did a whoopsie poopsie. If you, after this, go back or take a logic course, I don't know if there's logic in political science, but you can go to philosophy or sciences and take the logic course as an extracurricular, not extracurricular. I'm not sure about your student plan, but they should count as an optative course. I think that's the term. Optative, optional, I don't know. Curso optativo in Spanish. Yeah. You should be able to get them. Or if you have nothing better to do, just join them as a listener. And you should be able to clear that course, no problem. Anyway, so this one's also really fucking evil. This is the simplification to our more readable syntax. And this says, for everything that is a person, then there are at least two things, Y and C. Y and C are not the same. And for everything else such that this thing is a parent of the first person I was talking about, then rough. Then if you're a parent of X, then you're either the first thing, the first Y, or the second thing, the Z. Which is extremely awkward way of saying. For every person, there are at least two different things, such that for everything that is a parent of the first person, the X, all the other things that are parents of X are either one or the other parent of the person. Which is an extremely awkward way of saying every person has exactly two people as parents. This is how we count in predicate logic. We say, there are two things. These two things are different from one another, and they are defined by a singular property such that everything that fulfills the property is either the first thing or the second thing. And the first thing and the second thing are not the same. That is how predicate logic counts to number 2. It is kind of tricky, but it can be done. And I mean, it's not something we're going to delve on too much for this today. Now, let's get to models. Now that we have a more cursory understanding of the language of predicate logic, we kind of have like a little toy example of, okay, I have these formulas. How do I interpret them in a way that I can do logic with them? That I can study arguments and calculate information flow and so on, which are all the cool things that we did with propositional logic. Okay, so in propositional logic, we had truth functions. We had like, okay, so imagine we have like P and Q and R. So we had truth functions such that P was given the value true, Q was given the value false, and R was given the value true. And this was the unit of our interpretation for propositional logic, truth functions. We assign to a function an arbitrary value, true or false, to each propositional letter. But we cannot do that in predicate logic because let me do a simpler example. Let's take one of the more basic sentences in the homework. Anyone who is persistent can learn logic. What does it mean for P of X to be true? P of X is not a full statement. It's not something that we can evaluate as true or false. It is not a full sentence in our predicate logic. It's a formula, yes, but it's not something we can evaluate. P of x is not something that can be true or false, but it is something that can be satisfied. And yes, I know there's lots of jokes we can do with that, and we will make them, okay? Basically, when you have a free variable like this, that variable is hungry. Let's take a step back. Let's talk about P of A, where A is a constant, making the most satisfying choice. Yeah, you got it. Where A is a constant that stands for Arnold. P of A is something that can be true or false. Remember, our predicate properties, we can model them. So this could be like writing a program that needs to produce certain output. No, because that is syntax. That is our proof theory. We are trying to do model theory. That's a very good insight. But no, not quite. We first need to explain in a more interpretation way before we get into the proof theory. A program that needs to produce certain output is basically how we understand proof theory in classical logic. So remember that we have defined, it's fine, don't worry about it. As I said, those are good intuitions. It shows that you're engaged, and that's way more valuable. So we have defined predicates as sets. And we have visually expressed sets as circles containing things. Now, this is just a visual metaphor, okay? Sets are not circles, and I mean, sets are abstract entities. They're not something we can represent visually. They're just aids for us to get our human brains working. So P of A is true if and only if the... Why does it keep taking away my color? The object A is inside the set P. If A under the model is in P, then this is true. If A is outside or not in P under the model, in case it will be model 2, then P of A is false. So, predicates for constants are true or false depending on the model such that the model assigns A, or any particular constant, membership in the property set that we are inquiring about. Like I can just do this. See? For constants, it's a little more simple. Now, let's try an formula with a scoped quantifier. Let's try the statement. There exists an x such that p of x, and this is p, and we're gonna build our universal set. Or domain. So this is our domain. Looks like a face. Let me just use let me see like what the actual symbol is so I can visually. Now, there's a reason why many people don't like calling it a universal set. We're gonna get into that way later, but sooner than we all think. Oh, okay, I saw it. But yeah, there's the reasons. It's like a sassy U. That is the U of the universal set. Yes, it looks like a face. So, as usual, the models I tend to use for illustration examples, they tend to be very small, like 1 to a 3. When I need this time to use A, B, and C. So I'm just gonna talk about three things: A, B, and C. Arnold, Benedict. Whoops, let me. Or Ben. And Chris. Arnold, Ben, and Chris. Okay? Intuitively, what will make this formula true? There exists at least something that is P, in this case, persistent. As long as P has any object, whether it is A, B, or C, this is true. The only way this is false is if P is empty. And we have a specific symbol for the empty set, which is this symbol. If P is the empty set, then this is false. Now, for all x, P of x. What will make this formula true? It should be very intuitive at this point. If I am saying that everything is P, what needs to be the case in the model for everything is P to be true? If my domain is A, B, and C, which elements need to be members of P? You have 10 seconds until I find the clip. Exactly!
I told you. Benny.
This formula is saying, bring me everyone. Everyone! So who needs to be inside P? Everyone. Every single element of our domain needs to be inside of P. If A, B, and C are members of P, then this formula is true. Now, check this out. If there exists at least one element that is not member of P, which we will represent as this. There exists at least one who is not P. So this one is true only if everyone is a member of P. The counter will be if there exists at least one element that is not a member of P. Not P is therefore kind of like what in Venn diagrams they call the complement of P. So not P is everything not a member of P, everything outside P. So in this model, for every x, P of x is true. And in this model, there exists a P there exists an x such that x is not a P is false. Hell yeah. So if I change the model and I take C away from P, this formula stops being true and is instead false. False always under the model, and this formula will be true. Okay, now let me go the fuck back. There we go. This is fine. Now let's look at like an actual complex formula. Anyone who is persistent can learn logic. So I'm gonna need the L set. What this formula is saying is that if you are in the P set, then you are in the L set. For who? For everyone. But not everyone, just everyone who is in the P set. Let's look at this example. A is persistent and B is persistent. C now, C is not persistent. Now let's say that A can learn logic and B can learn logic. Is this formula true? Is it the case that for every P of X, then those things are also else? Everything that is P, if you're a P, then you're also on an L? Add. Oh, I'm so sorry. I really don't know what's going on because I'm pretty sure I keep telling Twitch I only want you to show ads when people log into the streams, not during the streams. But anyways. Also, I should set up Nightbot to tell me when the ads are rolling then. Ah, well. Let me draw the formula here as well. Are the ads done? Please tell me when the ads are done. Okay, cool. So we have this formula. For everyone that is persistent, then that person can learn logic. We're talking that this rule or this sentence applies to everyone. A way of seeing this is that a universal quantifier is like a wild card, a joker, if you will. So for every element of the domain, we're going to make an instance of this formula. Okay, we have exhausted all possibilities because we only have 3 elements in our domain. Now, the reason why this approach is limited and not rigorous enough is that, remember, we could have an infinite amount of elements in our domain. But in our toy model, let's see if this sentence is true for all possible cases. Is it true for case number 1? If A is P, then is it also true that L is A? Yes, look, A is in P and A is in L. So it is true that A is in P and it is true that A is in L. True implies true using the material conditional? Yes! The only case in which the material conditional is false is when the antecedent is true and the consequent is false. But that is not the case here. Let's check our second case. Is B of P true? Yes. Let me change color. Yes, it is true. B is inside P, is a member of P. It is also true that B is a member of L. Yes, look, here it is. So, both of these statements are true, and therefore the conditional is true. Is C a member of P? No, C is outside. So this statement is false. But is C a member of L? No, it's also false. But in the material conditional, false implies false is also true. The only case we don't want for the material conditional is for true to imply false. This we don't want. So I have scoured every possible case, every single element in my domain. So because it is true for every element of my domain for every x, then it is true for the quantifier. And the formula is true. That is how we evaluate formulas in predicate logic. We evaluate them through models. The problem is that we don't want this formula to be true just for this model. This formula needs to be true for all models. And here's where I'm going to need some definitions. Actually, before I do that, let me provide a counterexample. I need to prove that there is at least one other model in which this formula is false. And that is very simple once you have the adequate training. Once you have installed Cyberbrain Autistic Mode, you can just think of counterexamples. If I move C here, but not here, then there is at least one case in which someone is persistent, but they cannot learn logic, which is false, but we're just making stuff up. This model will make this true, this false, and therefore this conditional will be false. So there is at least one instance in which this formula fails, which makes it false. False under this model. So, because there is at least one model in which this formula is true, and at least one model in which this formula is false, we call formulas like this contingent. I'm gonna write it in chat. Contingent. And for the next part, I'm gonna need some, I need to go back to the book. I need some logical rigor. But I hope this serves like a general intuitive view of what models are and how they work. So these drawings and stuff, they're good for, you know, getting people to understand, getting people used to the idea of models and so on. But models are not drawings. Models need to be defined somewhat rigorously, especially because we're talking about sets of models that can be highly abstract and practically infinite. So let's use a more rigorously defined set of rules. Let L be a first-order language, like the one we're using. An interpretation M of L consists of the following ingredients. A non-empty set D, called the domain of the interpretation, or universal set if you want to call it that. And for each predicate letter, so in this case it's A, N of J, because they're using like computerized form, but in our language we use P's for properties and relationships and so on. For each predicate, an assignment of an n-place relationship in D. So what that means, if the predicate requires only one element, so in the case it's just like a P of n like this, then the n-place relationship is of 1. If it requires 2, then the n-place relationship is of 2, and so on. So basically, each predicate is going to be filled with the type of elements it requires. Properties of one's place will be required by just sets with elements with no order. Relationships that require 2 elements will be filled with ordered pairs. Relationships of 3 spaces will be filled with ordered triplets, and so on. Ordered quadruples, quintuples, if necessary, and so on and so on. It is almost never seen, or we rarely go beyond 4. Just know that it can be done. For each function letter of L, an assignment of n-place operation in D. So if we have functions, remember that functions are just ways of finding specific constants. So if we have a function of 1, then D is going to have a function set from the domain. Well, I mean, just for it has to be from the domain. 2 elements. So if the function is of 2 inputs to 1 output, then it's going to be from the Cartesian product of the domain to a codomain. And for each individual constant, an assignment of some fixed element. Yeah, that's going to be obvious. We have constants such as A, B, and C for Arnold, Ben, and Chris. Then we're going to assign them one specific element and only one specific element. Now, clever viewers or viewers that already know what functions are in a more intuitive way will know, hey, but C and D are the same thing. Yes. Because this is just a function. A unary function for all constants to elements of the domain. Given such an interpretation, variables are thought as ranging over the set D domain, and negation and implication, and this is because we're using the minimized language for definitions here, but remember that we can define conjunction, disjunction, and biconditional with just these 2 elements, so no problem, we can expand if necessary. And quantifiers are giving their usual meaning. Remember that an n-place relation in D can be thought of as a subset of D and the set of all n tuples of elements of D. So yeah, the set of all n tuples is the products of D. For example, if D is the set of human beings, then the relation father of can be identified with a set of all ordered pairs xy, such that x is the father of y. Here we understand father to be biological father, and unless we start getting into some biopunk shit, which is more encroaching the more we advance, so far human beings have one and only one biological father. But I think we're going to have to think of a new example pretty soon, because I don't even like the phrase biological father anymore, because it sounds too close to the stupid bullshit term of biological woman, whatever the fuck that means. I mean, all women are whatever, you know what I meant. So yeah, it's an increasingly unfortunate example in our more sci-fi life, but that's not the important part. For a given interpretation of a language L, a well-formed formula of L without free variables So remember, things that are not the type of P of X. P of X, because there's no quantifier here, has free variables. And free variables, formulas with free variables cannot be true or false. I mean, they can, but only under very specific circumstances. But for the most part, they can be satisfied or non-satisfied. There we go. Whereas a well-formed formula with free variables may be satisfied. Not really true. It's not the same. Satisfied is not the same as true, okay? Here the book is kind of fucking around with us. Represents a position that is true or false, whereas a well-formed formula with variables may be satisfied for some values in the domain and not satisfied for the others. The trick is this. Imagine a formula P of X or not P of X. This formula, which is not a sentence because it has unscoped quantifiers. Satisfied is when the redstone path completes a circuit to a card containing mystics and whatnot. No, sorry, redstone is propositional logic. This is way more advanced. So this is a formula, it's not a sentence. And this one is either satisfied or not satisfied. Same with this. But this entire thing is logically true. Because regardless of whether the formulas are satisfied or not satisfied, a formula of the type P or not P is always true for any model, no matter what. So I can get truth out of free variable formulas as long as the formula, the complete formula, is a logical truth. Or has the structure of a logical truth. Basically a theorem. So the idea is this. I know this is always true because if this formula is satisfied, then this one is not satisfied. But if this formula is satisfied, then the disjunction is true. If this formula is not satisfied, then this formula is satisfied, and then the disjunction is true. So, by collapsing model theory into truth functions, in a way, I can get logical truth for predicate logic. Consider the following well-formed formulas. Consider a relationship 1 of two spaces, x1 to x2. For every x to x2, and there exists a thing such that that thing is in the relationship A towards all things. Let us take as domain the set of all positive integers and interpret A as greater or equal than, less or equal than. Then well-formed formula 1 represents expression for every two integers there is at least one that is less or equal to another, which is satisfied by all the ordered pairs of the positive integers such that A is less or equal to B. So, even though this formula has free variables, hell yes, clicking! It doesn't matter which element we replace x or x2. If we define the relationship as less or equal to, then it is always true regardless of quantifiers. Well-formed formula 2 represents the expression for all positive integers x2, x1 is less or equal to them, which is satisfied only by the integer 1. Remember that here satisfaction is feeling an empty or open quantifier, a non-scope quantifier, with any element of our domain in a list. So if you notice, any element sounds a lot like an existential quantifier, right? Doesn't it? So yes, it is satisfied by only one element. Sure. Well-formed formula tree is a true sentence asserting that there is a smallest positive integer, in this case 1. If we were to take as domain the set of all integers, then well-formed formula tree will be false. Because integers also include the negative numbers. So we make things more complex. Yeah. Satisfied can be, if you need a mnemonic, think of it like unscoped quantifiers as being hungry. They need to eat an element of the domain. If the element of the domain they eat makes the formula true, then the formula, the original formula with the open quantifiers, is satisfiable. Satisfiable then is not the same as true. True, in first order logic, is satisfiable by all models. And with that, I think we have a very good introduction to models and domains. I am going to assign... this is too complex, too wonky. I'm going to assign some like circle exercises in the Discord as homework. Anyways, that is good enough for today. We are going to continue next week with actual... Now we're gonna continue with three proofs for predicate logic. Good night, Rupert. It's always a pleasure having you around. Have a good night, everyone. Have a good night, people who watch the video archives. You people also help me a lot. Have a wonderful time zone, everyone. And yes, that is everyone. Goodbye.